Hello everyone, this is Sir Marvin. So today, here in Advanced Engineering Mathematics for Civil Engineers, we're going to discuss the first part of our Lesson 1, which is complex numbers. So for this topic, we will have the following intended learning outcomes. So the first one is, students should be able to perform operations of complex number. The second one is to transform rectangular form of complex numbers to polar, trigonometric, exponential form, and vice versa. So let's start. So let's first define what is complex number. So a complex number, it is a combination of a real number and an imaginary number. So let's also define what is a real number and what is an imaginary number. So real numbers include rational and irrational numbers. So any number that we can think of is actually a real number. So that includes rational and irrational numbers. So rational numbers, these are numbers that can be expressed in ratio. So this includes whole numbers. This includes positive and negative integers. Okay, this also includes fractions, decimal numbers, etc. Okay, while irrational numbers, these numbers cannot be expressed into ratio. Okay, so this includes radicals, even pi and Euler's number are irrational numbers. Now, for imaginary numbers, these numbers don't really exist. So there's no solution in the real number system for imaginary numbers. So imaginary numbers are expressed with an I unit. Okay, so we use I as the unit for imaginary numbers. So you would know that it is an imaginary number if it has that unit I. Okay. So now let's talk more about imaginary numbers. So let's find out where we can find imaginary numbers. Okay, so consider the quadratic equation. So this is x squared plus 1 is equal to 0. If we're going to find the solution for x squared plus 1 is equal to 0, okay, we have to solve for the value of x. So solving for the value of x, that will be x squared is equal to negative 1 since we transpose 1 from the left side to the right side. So it will be opposite in sign. So that will be x squared is equal to negative 1. So solving for the value of x, so we can square root both sides of the equation. So that will be x is equal to positive or negative square root of negative 1. Now, if we're going to think of it, okay, if we go back to x squared is equal to negative 1, okay, so if we're going to think of a value that we can substitute for x and we squared that, okay, so, and it will give you negative 1. So if we think of a number, okay, that we can square, okay, that can give negative 1, there's no such number. Okay, so if you think of, let's say, positive 1, and you square that, that will give you positive 1. Okay, and if you also square negative 1, that will also give you a positive 1. So it won't give you negative 1. So it meaning to say, there's no number, okay, that when you square it, will give you negative 1. So meaning to say, it has no solution. Okay, it doesn't exist. Okay, so yung x natin, which is equal to positive or negative square root of negative 1, yan ay pwede nating sabihin na yan yung I. Okay, so square root of negative 1 is equal to I. Okay, so there's no solution in the real number system for this number, no? So this is the imaginary number. Okay. So it is important to take note of these values, no? That I is equal to square root of negative 1. So if you square that, that will be I squared is equal to negative 1. So you have to memorize this, no? So we're going to use this in the succeeding topics. Okay. So similarly, if we consider x squared plus 16 is equal to 0, if we're going to find for the solution for this quadratic equation, we have to solve for the value of x. So solving for the value of x, that will give you x squared is equal to negative 16. And solving for the value of x, we have to square root both sides of the equation. So it will give you x equal to positive or negative square root of negative 16. So as we know, square root of negative 16 has no value, right? So even if you input that to your calculator, no, it won't give you an answer. So there's no solution for square root of negative 16. Okay, but if we're going to apply one of the laws for radicals, we can actually factor out square root of negative 1 from square root of negative 16. So that will give you square root of 16 times square root of negative 1. So this is also equivalent to square root of negative 16. So solving for this, as we know, square root of 16 is actually equal to 4. And square root of negative 1, this is actually equal to I. So therefore, we can say that x is equal to positive or negative 4i. So this will be the value of x for this quadratic equation. Okay, again, so let's consider the following quadratic equation. So this is x squared plus 2x plus 10 is equal to 0. So this is a different quadratic equation compared to the quadratic equations that we solved earlier. No, so this has a middle term. Okay, so for this quadratic equation, if we're going to find for its solution, so to solve for the value of x, we can use different methods. We can actually use quadratic formula. We can also use factoring, no, if this is exact, okay. But if it's not exact, okay, it will be difficult, okay, to solve that using factoring. Okay, so let us use quadratic formula instead. Okay, so if you're going to recall your quadratic formula, so that will be x equal to negative b plus or minus square root of b squared minus 4ac over 2a. Wherein yung a, b, and c natin, we can find that in our quadratic equation. So for the value of a, that will be the coefficient of your x squared, which is 1. Okay, so for your b, that will be the coefficient of your middle term, which is 2. Right? So for the value of c, that will be the constant, which is 10. Okay, so substituting these values to the formula, so this will give you x equal to negative 2 plus or minus square root of 2 squared minus 4 times 1 times 10 over 2 times 1. So simplifying that, okay, so simplifying that, it will give you negative 2 plus or minus square root of negative 36 over 2. So again, square root of negative 36 has no solution. Okay, so there will be no value for that, but we can use a law of radical for that, that we can factor out square root of negative 1 from square root of negative 36. So factoring that out, so that will give you square root of 36 times negative 1. Okay, so the new value of x will be equal to negative 2 plus or minus square root of 36 times square root of negative 1 over 2. So as we know, the value for square root of 36 is just 6. Okay, and the value for square root of negative 1 is I. Okay, so simplifying this further, so this will be x equal to negative 2, square root of 36 is 6, and then square root of negative 1 is I over 2. So we can simplify this further. So factoring out 2, okay, from the equation or from this, okay, so it will give you negative 1 plus or minus 3i. So this will be the values of x for this quadratic equation. Okay, so as we can see, there's an imaginary number for this solution, right? So from here, we can say that for quadratic equation, if b squared is less than 4ac, the value of x will have an imaginary part. Okay. Okay, so as we can see in our quadratic equation, our b is 2, right? So b squared is 2 squared, that will be 4. And yung 4ac nga natin, that will be 4 times a, which is 1, times c, which is 10. So ito yun, no? Dito yun galing. So that will be 40. So as we can see here, 4ac is greater than b squared. So therefore, it will really give you negative, okay, a negative answer. So if you square root a negative number, so again, that will have no solution. Okay, so it will really produce an imaginary part. So for this solution, okay, for the values of x, there's an imaginary part here. Okay. Okay, so let's talk about now the scalar functions of complex numbers. So from the general form again, so the general form is z is equal to a plus bi. So from this form, this quantity a is actually called the real part of complex number z. Okay, so that will be the real part of complex number z, and it is denoted by re, open and close parenthesis of z, is equal to a. So again, your a will be the real part of your complex number z. Now for b, okay, for the quantity b here in your general form of complex number, so this will be the imaginary part. Okay, so your imaginary part, it will be denoted by im, open and close parenthesis of z. Okay, so that will be the imaginary part of complex number z. Now, there are also cases, okay, that your real part is 0. Okay, so if your real part here is 0, so your complex number will become z is equal to bi. So that is still a complex number. Okay, even if it only includes or involves imaginary parts. So that is still a complex number, but that complex number is purely imaginary. Okay, now, what if your imaginary part here is 0? Okay, so what will remain here is z is equal to a. So the question is that complex number, if it is z is equal to a, only real part, okay, is that still a complex number? The answer is yes. So even if the complex number only has a real part, okay, and the imaginary part is 0, so that is still a complex number. So generally, all real numbers, okay, are complex numbers. Okay, so for that kind of complex number, that is called purely real, okay, complex number. So that's still a complex number. Now, we also have what you so-called magnitude of complex number z, or modulus of complex number z. So it is denoted by z with absolute value symbol here, or it can also be denoted by just r. Okay, so it is the modulus or magnitude of z, and it is given by square root of a squared plus b squared, wherein your a will be the real part and b is the imaginary part of your complex number. Now, for a conjugate of your complex number, it is denoted by z bar, and it will be a minus bi. Okay, so if your given complex number is z is equal to a plus bi, its conjugate will you're just going to change the sign before the imaginary part of your complex number. So this positive sign will just be negative. So this will now be your conjugate. And it will also work vice versa. If your given is a minus bi, if your given complex number is a minus bi, its conjugate is a plus bi. So you just really have to change the sign, okay, before the imaginary part, and that will be the conjugate of that complex number. Okay, now we also have argument of your complex number. So for the argument of your complex number or phase of complex number z, okay, so that is denoted by arg, open and close parenthesis of z, or theta. Okay, simply theta. And it is given by this formula, arctangent of b over a, wherein b is the imaginary part and a is the real part of your complex number. But actually, your argument, okay, the argument for complex numbers, it's not always arctangent b over a. So it depends on the location of the quadrant, okay, of your complex number. So later on, I will discuss that on the succeeding slides. Okay, so for our arguments, okay, it can be expressed in radian or degree. But here's the thing, for this course, okay, for this term, okay, we're going to use radian. So for all the computations, okay, for all the computations of argument that we're going to do, okay, here in this course, we're going to use radian. So as soon as now, you have to turn your calculator to radian mode. So see to it that it is in radian mode, because if it's in degree mode, okay, it will give you the different answer. So that will be wrong. Okay, again, the arguments here for our course will all be in radian. Okay, take note of that. Now, let's proceed to the powers of I. So the powers of I is given by this derived equivalents, no? So I raised to 4n is equal to 1, I raised to 4n plus 1 is equal to I raised to 4n plus 2 is equal to negative 1, I raised to 4n plus 3 is equal to negative I. So for I raised to 4n, it means that the exponent of I here, or the power of I here, is divisible or exactly divisible by 4. So if that is divisible exactly by 4, so it will be equivalent only to 1. Now for I raised to 4n plus 1, let's say you have a power which when you divide by 4 has a remainder of 1. So that will be I. Okay, and if you have a power of I, wherein if you divide that exponent or power by 4, and it will give you a remainder of 2, so that will give you a negative 1, okay, as an equivalent. And for I, or power of I that has exponent that when you divide by 4 has a remainder of 3, so the answer for that will be negative I. Okay, so let's find out where we have derived this equivalence, no? So let's consider this. So I raised to 1, let's say, we know that that is I. Okay, so and it is also equivalent to square root of negative 1. And also, I squared, as we know, that is equivalent to negative 1. Now, if we're going to proceed to I cube, so that will be I cube, no? So we can factor this, no, into I squared times I. So that is also I cube, right? And we know that the value of I squared is negative 1, and the value of I is I. So simplifying this, negative 1 times I, that will be negative I. So now we know that I cube is equal to negative I. Now for I raised to the fourth power, so we don't know yet what is the value of I raised to the fourth, but we can factor this out into I cube times I, right? And we know that the value of I cube is negative I. Okay, as we have derived this from here. Okay, and the value of I is I. So we know that if we multiply negative I to I, so that will give you negative I squared. And we know that the value of I squared is negative 1. So negative times negative 1, that will be positive 1. So now we know that the value of I to the fourth power is I. So continuing this, no? So let's say I raised to the fifth. So if we're going to solve for I raised to the fifth, we can factor this out into, or we can factor this into I to the fourth times I, wherein we know that I to the fourth is 1 and I is I. Okay, so 1 times I, that will give you I. So we now know that I to the fifth is actually I. Okay, so now continuing this, so let's say I raised to the 6. So to solve this, we can factor it into I to the fifth times I. And we know that I times I, or we know that I to the fifth is actually equal to I. Okay, so I times I, that is I squared. And we know that I squared is equal to negative 1. So again, if we continue this further, so let's say I raised to the seventh power. So that will be I to the 6 times I. So we know the value of I to the 6, that is negative 1. So if you multiply that to I, that will give you negative I. So now, if we proceed again, so let's say I raised to the 8th power. So to solve this, we factor this into I raised to the 7 times I. And we know that I to the 7 from here is negative I. So that will be negative I times I is equal to negative 1 squared. So that will be equal to negative times negative 1 is equal to positive 1. So here, if we're going to continue this further, okay, what if we are going to solve for I raised to 2005? Let's say that's the power. So if we continue this on, it will be it will be difficult, okay, and it will be a long solution. Okay, if we continue this solution, no. So from here we can actually derive a conclusion, okay, that as you can see here, um, it just from here to I to the fifth, okay, the answer for this just go back, okay, or just went back to the first I, which is I raised to the first power, and then here in I to the sixth, this is just the same here, right? To I squared, which is negative 1. And then I to the 7, it's just the same with negative I, which is I cube, right? So, and I to the 8 is also just the same as I to the 4th. And if you continue this on, if you solve for I raised to the 9th power, you can notice that the answer will just be I. Okay, so from here, we can draw a conclusion, okay, that for every 4 interval, or for every fourth interval of the power of I, okay, so it just creates a loop of values that just continue on. Okay, so from that, no, we can say that if a power can be divided by 4, okay, so that will automatically give you a value of 1. Okay, and if you divide that exponent by 4 and it give you a remainder of 1, so that will just give you I. Okay, and if you divide that exponent by 4 and gives you a remainder of 2, okay, so that the value for that will be negative 1. Okay, and for exponents that when you divide by 4 and gives you a remainder of 3, so that will be negative I. Right? So, yun yung mga yun, no? Yun yung mga values natin for this. No? So, let's solve the examples for this problem. Okay, so let's solve the following examples. So the first one is I raised to 2,307, and the second one is I raised to negative 25. So let's solve the first example. So this is I raised to 2,307. So to solve this, okay, we just have to divide first, okay, the power of I, which is 2,307, by 4. So if you divide that by 4, so that will give you 76 point something, right? So it means that there's a remainder. So the remainder for that, so 4 times 576 is actually 2,304. So there's a remainder of 3. Okay, so from here, no, we can say that I is equal to 4 times 576 plus 3. So from the derived equivalent from the previous slide, we can say that the value for this is actually negative I. But simplifying this further, we know that I raised to 4 times 576 times I raised to cube is equivalent to this, no? So this is one also of the laws for exponent, no? That we can factor this out this way. Okay, so as we know that I raised to 4 times 576, that is equivalent to I raised to 4n. So that is 1, right? And I cube, as we know, that is equivalent to negative I. So 1 times negative I is just negative I. So for this example, this is the answer. So the equivalent of I raised to 2,307 is negative I. So that will be the answer. Now, for the second example, this is I raised to negative 25. So, if we're going to solve this, we have to make the exponent here, which is negative, no, we have to make this positive. Okay, so to make this a positive power, okay, we just have to put this in the denominator. So 1 over I raised to 25 is actually equivalent to this, right? So this is also a law for exponent, that if you put that in the denominator, the sign will be opposite. So I over or 1 over I raised to 25 is equivalent to this. So solving this now, so this will be equal to 1 over I raised to 25. So we just divide 25 by 4. Okay, so dividing 25 by 4, that will give you 6 point something, right? So there's a remainder again for this. So the remainder for this is 1, right? Because 4 times 6 is 24. So the remainder is 1. Okay, and we know that for exponents, that when you divide by 4 and has remainder 1, okay, the value for that is I, right? So this will become 1 over I. And for this is actually a division of complex numbers, 1 over I. So we haven't discussed that yet, no? The division for complex number. So we haven't discussed that yet. But the rule for that is you just have to multiply this fraction, okay, by a fraction okay, wherein the numerator and the denominator is the conjugate of this denominator. So the conjugate of this denominator is negative I. Okay, so that will be negative I over negative I. Okay, so negative I over negative I is actually equivalent to 1. So basically, we did not change the given for this because it's just, it will just be multiplied by 1. Right? So, performing this, so 1 times negative I is negative I, and or I times negative I, that will be negative I squared. So, simplifying this further, so that will be negative I, and we know that I squared is equivalent to negative 1. So, that will be negative 1 times negative, so that will be positive 1. So, that will just be negative I. So, the answer for number 2 is also negative I. So, that will be the answer. So now let's proceed to the fundamental operations for complex numbers. So the first operation is the sum or addition of complex numbers. So that will be z1 plus z2. Let's say z1 is a plus bi and z2 is c plus di. So the rule here, if you add up two complex numbers in general form, so you're just going to combine the real part to real part and imaginary part to imaginary part. So performing this operation, so we just add the real part. So the real part for this complex number is a, so that will be a, and here the real part is c, so that will just be a plus c. So ito yon. Okay, and also you just have to combine the imaginary parts. Okay, so for this complex number, the imaginary part is bi, and here the imaginary part is di. Okay, so adding that up, okay, so that will be bi plus di. Okay, and factoring out I, so that will just be b plus d. Okay, so it's also the same when it comes to subtraction or difference of complex numbers. So let's say z1 minus z2, that will be a plus bi minus c plus di. So you just have to subtract the real parts and subtract the imaginary parts. Okay, so here the real part again is a, and then here the real part is c, so that will be a minus c. So ito yon plus. Okay, so here the imaginary part is bi, and then here the imaginary part is di. So subtracting that, that will be bi minus di, and then factoring out I, that will give you b minus d. Okay, now for product, okay, of complex numbers, so that is z1 times z2, and that will be a plus bi times c plus di. So the rule here, it will actually just use FOIL method, okay, to derive this. So you don't have to memorize this, okay, this formula for product. Okay, we just used FOIL to derive this. So I'll show you later, no, how we have come up to this formula. Okay, now for quotient of complex numbers, so that will be z1 over z2, or a plus bi over c plus di. Okay, so this will be the derived formula for this quotient. But again, you don't have to memorize this, no? So in the next slide, I will show you how we have come up to this formula. Okay, so let's derive now the formula that we have for product of complex number. So for product z1 times z2, so that will be a plus bi times c plus di. So we're going to use a FOIL method here. So FOIL stands for F for first, O is outside, I is inside, and L is last. So using FOIL method, we just multiply the first term for the two complex numbers. So that will be a times c. And then we multiply the outside, which is a times bi. Okay, and then we multiply the inside, which is bi times c. And then we'll multiply the last term of both complex number, which is bi and di. So ito yun. So ac plus abi plus bci plus bdi squared, wherein I squared, as we know, that is equivalent to negative 1, right? So simplifying this further, okay, this will become AC plus ABI plus BCI minus BD. So combining all the real terms, okay, or the real parts and the imaginary parts, so that will be AC minus BD. So ito yon. And then we have ABI plus BCI, which when we factor out I, that will become AB plus BC. So this is the formula
okay, written from the previous slide, okay, for product of complex numbers. So you don't have to memorize this, ha, or you just have to use FOIL method. Now, for quotient, okay, for quotient Z1 over Z2. Okay, so the rule for this, okay, the rule for division of complex numbers in general form, you have to multiply this given, okay, which is Z1 over Z2, by a fraction wherein the numerator and the denominator is the quotient of this denominator. So the quotient for this is Z2 bar over Z2 bar. And we know that Z2 is C plus DI, right? And Z1 is A plus BI. So the conjugate of C plus DI is C minus DI. So that will be C minus DI over C minus DI. So again, this will just be equal to 1, right? So we didn't really change the given, right, by multiplying this fraction. So this is just equivalent to 1. Okay, so from here, so this will be division of fractions. So we just apply the rule for division of fractions. That will be numerator times numerator, and then denominator times denominator. So for numerator times numerator, so we will just apply FOIL method here since this will be product of complex number. So that will be AC minus ADI plus BCI minus BDI squared. So same here with C plus DI times C minus DI. So that will give you C squared minus CDI plus CDI minus D squared times I squared. Wherein you know here that minus CDI plus CDI will just be cancelled, right? So what remains here will be C squared plus D squared. And then simplifying this, so this will be AC plus BD. So we know that BD times I squared will just be equal to BD because I squared is equal to negative 1. So negative times negative, that will be positive. That's why it became positive. Okay, plus combining the imaginary parts, which is ADI plus BCI, so that will be BC minus AD times I. Okay, so this is the formula that is written in the previous slide for quotients or for quotient of complex numbers. So you don't have to memorize this, you just have to apply our rule. Okay, so that you just have to multiply, okay, this fraction by a fraction wherein the numerator and the denominator is the conjugate of this denominator. So that is the rule for quotient for complex numbers in general form. So now let's solve the following examples. So we have here complex number z1 is equal to 3 plus 5i. We have z2 is equal to 2 minus 7i. So we are asked here to find number 1, z1 plus z2, number 2, z1 minus z2, number 3, z1 times z2, and 4, z1 over z2. So solving number 1, okay, so for its solution, so we just have to apply the rule for addition of complex numbers in general form. Okay, so this will be 3 plus 5i plus 2 minus 7i. So combining the real part, okay, so that will be 3 plus 2. So that will be 3 plus 2. And then combining the imaginary part, which is 5i plus negative 7i. So that will be 5i minus 7i. So simplifying this, so this will become 3 plus 2 is 5, and 5i minus 7i is negative 2i. So that will be the answer for number 1. Now, for number 2, so this is z1 minus z2. So that will just be 3 plus 5i minus 2 minus 7i. So combining the real part, that will be 3 minus 2. So that will be 3 minus 2 plus combining the imaginary part, that will be 5i minus negative 7i, which will become positive, right? So that will be 5i plus 7i. So simplifying this, 3 minus 2 is 1, and 5i plus 7i will be 12i. So that will be the answer. Now, for the third uh, question, so that will be z1 times z2. So this will be product of complex numbers. Okay, so this will just be 3 plus 5i times 2 minus 7i. So here, we're just going to solve this using FOIL method. So you don't have to memorize again the formula here, ha? Okay, so we just have to apply FOIL method. So that this will be 3 times 2, that will be 6. and then 3 times negative 7i, that will be negative 21i, and then 5i times 2, that will be positive 10i, ito yun. Then we have 5i times negative 7i, which will be negative 35 raised to, or times I squared, right? So from here, no, we can say that negative 35i squared is just equal to positive 35 because I squared is just equal to negative 1. So negative 1 times negative will be positive. So combining all the real parts, so that will be 6 plus 35. So ito yun. Okay, so that will be 6 plus 35. And then combining the real parts, that will be negative 21i plus 10i. Ito yun. So 6 plus 35 is just equal to 41. And then negative 21i plus 10i is just equal to negative 11i. So that will be the answer. Now, for the fourth question, that will be Z1 over Z2. So again, our rule for quotient for complex number, so that will be 3 plus 5i over 2 minus 7i. So our rule is that we multiply this fraction, okay, by a fraction wherein the numerator and the denominator is the quotient, is the conjugate rather of the denominator here. So 2 minus 7i, the conjugate of this is 2 plus 7i. Okay, so the conjugate is just changing the sign before the imaginary part, right? So the conjugate of 2 minus 7i is 2 plus 7i. So that will be 2 plus 7i over 2 plus 7i. So this will just be equivalent to 1. So we really didn't change this given. Okay, so multiplying these two fractions, so this will just be numerator times numerator, and then denominator times denominator. So we apply again FOIL here because it will be product of two complex numbers. So 3 plus 5i times 2 plus 7i. So this will be the result. Okay, so this will be 6 plus 21i plus 10i plus 35i squared. Wherein 35i squared, we know that this is just equal to negative 35 since I squared is equal to negative 1. Now for the denominator, so this will be 2 minus 7i times 2 plus 7i. So the result here will be 4 plus 14i minus 14i minus 49i squared, wherein 14i minus 14i will just be cancelled. And then I squared will be negative 1 times negative, so this will become positive 49. So simplifying this, so this will become 6 minus 35, so that will be negative 29. So ito yun. And then we have 21i plus 10i, so this will be 31i, right? And then we have 4 plus 49 here, so that will be 53. So this will now be the answer for number 4. So now let's proceed to another fundamental operations for complex numbers. So these are sum of conjugates, difference of conjugates, and product of conjugates. So for sum of conjugates, that will be z plus z1. Let's say z is a plus bi. So the conjugate of this is a minus bi. So it's just simple that when you add two conjugates, it will just add the two real parts, okay, of the two complex numbers. Since bi plus negative bi will just be cancelled. So definitely a plus bi plus a minus bi will just be equal to 2a. So you don't actually have to memorize this then naman, no? Kasi it's obvious naman, no, that when you perform that operation, it will give you 2i. So same here with difference of conjugate, that will be z minus z bar. So a plus bi minus a minus bi. So if you apply the operation for this, a and minus a will just be cancelled, right? So ang matitira dito, what will remain here will be bi minus negative bi. Okay, that will be 2bi, right? So that will be the difference for conjugates. And now for products of conjugates, so that will be z times z bar. That will be a plus bi times a minus bi. So here, we actually encountered this in our examples for quotient, right? That what will happen here is the middle terms, which is a bi minus ABI will just be cancelled. Okay, so what will remain here is just a squared plus b squared. So we can directly get this value, no, a squared plus b squared, without using FOIL method when you know that you are multiplying conjugates, right? So that is directly a squared plus b squared. So now let's solve the following example. So this is z is equal to 3 plus 5i, and its conjugate is z bar is equal to 3 minus 5i. So we are asked here to, the first one is to find the sum of conjugates. The second one is to find the difference of conjugates and the product of conjugates. So for the solution for this example, for number one, that will be sum of conjugates. So that will be c plus z bar. That will be 3 plus 5i plus 3 minus 5i. So applying what we have discussed from the previous slide. So this will just be 6, right? That this will just be 3 plus 3, which is 6. Okay, so the second example is z minus z bar, which will be 3 plus 5i minus 3 minus 5i. So applying again the what we have discussed, okay, in the previous slide, this will be just 5i plus 5i, right? So 5i minus negative 5i is just 10i, right? So that's the answer for this. Now for product of conjugates, okay, so applying again what we have discussed from the previous slide. So for conjugates of or for product of conjugates, it will just be a squared plus b squared. So it will just be 3 squared plus 5 squared, which is 9 plus 25, and this will be equal to 34. So this will be the answers. So now let's talk about the different forms of complex numbers. So the first form is the component form or Cartesian form or rectangular form. So this is expressed by complex number z is equal to x plus yi. Okay, so this is actually the same with the general form of complex numbers, right? So for this form of complex number, we have Cartesian coordinates, where in the Cartesian coordinates is the real part and the imaginary part, which is x and y. So these are the Cartesian coordinates. Okay, so now if you're going to graph your complex number in component, Cartesian, or rectangular form, you can use Argand diagram to do that. Okay, Argand diagram or Cartesian complex plane. So we're going to use this to represent graphically our complex number. Okay, in component, Cartesian, and rectangular form. Okay, so here, this is just simple. Okay, so it's the same, okay, when you are graphing in a Cartesian plane. So in Cartesian plane, you actually have two axes. Okay, we're in here in Argand diagram or Cartesian complex plane, the x-axis will be your real axis, meaning to say, this will be the axis, okay, where you are going to plot the real part of your complex number. Okay, wherein, meanwhile, okay, your y-axis will be your imaginary axis. So this will be the axis where you are going to plot your imaginary part in the complex number. So let's say we have here complex number 3 plus 4i. So to graph this 3 plus 4i in this Argand diagram, so the real part for this is 3. So you just have to plot that, okay, in the real axis. So in the real axis, positive 3 is located here. And then the imaginary part will be 4i. Okay, and from the imaginary axis, okay, your 4i will be here. So tracing those point or that point, that will be located here at this point. So this point is the representation or graphical representation of 3 plus 4i. Now, let us also solve the remaining points that are plotted here in this Argand diagram. So for this point, okay, so let's find out, okay, what complex number it represents in this Argand diagram. So here, at this point, okay, the uh, real in the real axis, this is actually 2, right? And in the imaginary axis, okay, this is negative 3. So we can say that the complex number that it represents is actually 2 minus 3i, right? That will be 2 minus 3i, right? So this is the representation of that complex number. Now, for this complex number or for this representation here, graphical representation here, so let's find out what complex number it represents. So as we can see, in the real axis, this is negative 4. and in the imaginary axis, this is positive 2. So we can say that the real number is negative 4 plus 2i, right? So this graphical representation, this point actually represents negative 4 plus 2i. Now for this point, okay, so the complex number that it represents, since this is in the real axis only, so it means that its imaginary part is 0. So we can say that this imaginary or this complex number is just equal to 3. Okay, and for this point, okay, the complex number it represents is just in imaginary axis, right? So this is just an imaginary number. So we can say that this is a complex number equal to 4i. So that's how you represent graphically your complex numbers in component, Cartesian, or rectangular form. So we use Argand diagram. Now, for polar form, so this is the second form of complex numbers. So this is expressed, okay, or represented by z. Complex number z is equal to r, okay, angle theta. So this is not less than, ha. This is not a less than sign. So this is actually angle, okay. So this is r angle theta, wherein r is the modulus of complex number z, and your theta will be your argument, right? Okay, so to solve for r, that is again the magnitude or modulus of z. So it can be represented by r. So that will be equal to square root of x squared plus y squared. Okay, wherein yung x, that is the real part, right? And y is the imaginary part. Okay, so that's how you solve the magnitude or modulus of z, which is r. Okay, and your theta or argument, okay, of z, that will just be equal to arctangent of y over x, wherein yung y, that is your imaginary part, and then your x will be your real part. Okay, so yung radians, yung theta natin class, or yung argument of z natin, it will be expressed in radians, ha, for this course. So you have to at least give five decimal places, okay, in computing for theta. Okay, so and there's an important note here, class, that your theta will depend on the quadrant the complex number is located. Okay, so we're going to discuss this further, okay, in the succeeding slides, how to get or how to analyze your argument, okay, or your theta. So the next form of complex number is actually trigonometric form. So your trigonometric form is expressed as complex number z is equal to r cosine theta plus I r sine theta. Okay, wherein r again, that is actually your magnitude or modulus of z, and your theta is your argument. Okay, so it can also be expressed as z is equal to r cis theta. Okay, so you can solve for let's say the given is trigonometric form, okay, and you want to know the real part of that complex number. Okay, so the formula for that is just r cosine theta and y is equal to r sine theta. Okay, so let's talk about this more when we graph our this form of complex number. And the last form will be exponential form. So now for exponential form, this is expressed as z is equal to r e raised to I theta, wherein r again is the modulus or magnitude of z. Okay, and theta is the argument of z. Okay, and e here is actually a constant. Okay, so this is called Euler's number, and its actual equivalent is 2.71828183, and so on. So you can see that in your calculator. No, so that is a constant. So now let's talk about how we represent graphically the three forms that we have discussed: the polar form, the trigonometric form, and exponential form. So as you can see, okay, these three forms, okay, that I've mentioned, they have something in common. Okay, so they all have r and theta, right? So they all have r and theta. Okay, so to graph these three forms of complex number, we use a polar complex plane, okay, to represent them graphically. So this is used for polar, trigonometric, and exponential form of complex numbers. Okay, so if in Cartesian plane, okay, or in Argand diagram, okay, we use Cartesian coordinates, which are the real and imaginary part of the complex number. Here in polar complex plane, okay, we are going to use polar coordinates. So for polar coordinates, that will include your r and theta. Okay, now from here, okay, so this is actually the same axis or axis in Argand diagram. So your x-axis will still be your real axis and your y-axis will be your imaginary axis. Okay, so here the coordinates that we're going to use are r and theta. Okay, so for r and theta, okay, so this will be the point. Okay, let's say this imaginary number z is equal to r cosine theta plus I sine theta. So this point here, okay, when you connect that to the origin, okay, that will be your r. Okay, and the theta, okay, from the x-axis, okay, from the x-axis, that will be your argument. That will be your theta, right? So that's how you graph here in polar complex plane. But here, class, if we have given na r and theta, okay, to solve for the value of x and y, which are the imaginary and real part of a complex number, we can use this triangle, right? So we know that this is r, this is r, this is theta. So this side of this triangle is actually x. So that is the x or the real part, okay, of the complex number. And this vertical line here, okay, this side, okay, is actually y. Okay, so this is the imaginary part of the complex number. So if you're going to solve for x, okay, so that is just equal to r cosine theta, right? Because cosine theta is actually x over r, right? Cosine theta, this is the theta, so this is r, and this is x, right? And we know that cosine theta, that is in SOHCAHTOA, that is adjacent over hypotenuse, right? And the adjacent here is this. So this is x, right? And then this is the hypotenuse r. So solving for the value of x, so that will just be x is equal to r cosine theta. So cross multiplying that. So that will be r cosine theta. So that's how you solve the imagine or the real part of the complex number, okay, when it is in polar, trigonometric, or exponential form. That is just r cosine theta. Now, for y naman, okay, for the imaginary part of the complex number, okay, we can use sine theta for that. So sine theta is so opposite over hypotenuse. So here, the opposite is y. So this is the y. So ito yon. And then the hypotenuse here is r. So that will be y over r. And then solving for y, that will be r sine theta. So this is how you solve for the imaginary part of a complex number. Okay, if your given complex number is a polar, trigonometric, or exponential form. Okay, so let's continue on. Now the argument of complex numbers. So as I've mentioned earlier, that the arguments of complex numbers, they are dependent, okay, on the location, okay, of the quadrant of that complex number. Okay, so we have here the different locations, okay, of your complex numbers. We have here quadrant 1, quadrant 2, quadrant 3, and quadrant 4. Okay, so it is important to take note, class, that all the arguments, okay, of your complex numbers, okay, it's always measured, okay, or drawn from your positive x-axis. So in this axis, so it's always measured from here. Okay, and also, class, your argument, okay, cannot exceed 180 degrees. Okay, so it cannot be 181 degrees. Okay, also it cannot exceed, or it cannot be less than negative 180 degrees. okay, or negative pi. Okay, so it cannot be negative 181 degrees. It cannot be 182, negative 182 degrees. Okay, so that can't be, okay, for arguments. Okay, so if your complex number is located here in your first quadrant, okay, so the argument will be this angle. Okay, so this angle will be your theta or will be your argument. That if you're going to compute, okay, for this theta, so it will just be given with this formula. It will just be the arctangent of y over x. Okay, wherein you got it from tangent theta. Okay, so this will be the theta, and your y will be the opposite side, opposite to the theta. Okay, and this side will be the adjacent side. So this will be the side adjacent to the theta. Okay, so using tangent theta, so TOA, you will use TOA for that. That will be tangent theta is equal to y over x. That's why it is arctangent y over x here if we're going to solve for theta. So that will be the theta for complex number or argument, no, for complex numbers located in the first quadrant. Now, if your complex number is located in the second quadrant, so your theta again will be drawn from the positive x-axis. This will be a reference line. So this will be our theta. So it will be, again, it will be drawn from your x-axis, positive x-axis to the line, okay, or to the modulus. This is the modulus, no, to the modulus of the complex number. Okay, so that will be your theta. So now, if your complex number is located in the third quadrant, so let's say this is your complex number. So you cannot draw your argument, okay, from here. That your argument will be from here, and it will be rotated to this, okay, to the up to this point, because I've mentioned earlier that your argument cannot exceed 180 degrees or pi, right? That is pi in radian. So it cannot exceed pi. Okay, because if it's already here in the third quadrant and you rotate it from this positive x-axis this way, so this is counterclockwise, right? So it will exceed 180 degrees. So instead, okay, you will get the argument for complex numbers in the third quadrant if you draw it from the positive x-axis, okay, so in the direction clockwise. Okay, so your argument will be this, no, drawn from your reference axis, which is the positive x-axis. Now for your fourth quadrant, so this will be the your complex number in the fourth quadrant. So this will be your theta. Now for the argument in the second quadrant, so it can be solved, okay, by this formula. So it will be theta is equal to arctangent of y over x plus pi. So the thing here, class, is that if you're going to solve for arctangent of y over x for this complex number in the second quadrant, the angle that you're going to get will be this angle, right? So that this will be that angle, okay, and this angle is not the argument. Okay, again, your argument is this one. So it should be solved by this formula. Okay, so class, ganito ang mangyayari, no? So the angle here, okay, that you're going to get if you're going to use arctangent of y over x, since since one of the coordinates for that will be negative, that is the real number coordinate, no, or the x coordinate, okay, it will be negative since it's here in the second quadrant. So what's going to happen to your angle here, okay, if you use arctangent y over x, that will be negative, right? So this will be negative. So to solve for this, okay, for this theta, you just add pi, because if you add, your pi will be this whole angle, right? So 180 degrees or pi. So if we add this angle, which is negative, so it will give you the value of this theta. Okay, so class, for angles that are negative, okay, they are negative because from the reference axis or from the reference x-axis, okay, from this axis, let's say, okay, it will be negative because the rotation for this will be clockwise. So if the rotation of the angle from the x-axis, regardless if positive or negative x-axis, no, so it will be negative. So since this is clockwise from here, right? And also, for your argument in the third quadrant, okay, so since it is drawn here to here, so the rotation will be clockwise. So the value for the theta for the argument, okay, for the complex numbers in quadrant 3 will be negative. Okay, now for the formula for solving for the value of theta or argument for complex numbers in quadrant 3, so this will be given by this formula. So that will be arctangent of y over x minus pi. Okay, so now, if we're going to use arctangent y over x for this, no, so the angle that we're going to get is this angle. But this angle is not the argument. So again, the argument is this. So the angle here that you're going to get, okay, will be positive. Since from the x-axis, its rotation will be counterclockwise, right? Counterclockwise. So from here to here, it will be counterclockwise. That's why it will be positive. And also, the value of your y and x here is negative, both negative. So it will really give you positive, right? Positive angle. So from that positive angle, okay, so the value of this whole angle, no, from this axis up to this point, so that this will be negative pi since it is rotated clockwise, right, from here to here. So that will be negative pi. So that's why it is minus pi here. So the value of the angle here will be positive and this will be negative, and the answer for this will be the theta, and your answer here will be negative. Okay, so that's how you solve for the argument when the complex number is in the third quadrant. Now, if your angle or if your complex number is in the fourth quadrant, so your fourth quadrant is here, so let's say your point is here, so the argument will be this theta. So if you're going to solve for that theta, it's actually directly arctangent of y over x. Okay, so the thing here is that this theta will be negative. Since from this reference axis, it will be clockwise, right? So that will give you a negative angle. Okay, so that's how you solve for the argument, okay, for complex numbers in fourth quadrant. So that's how you solve the arguments for all the complex numbers, no, located in different quadrants. Okay, so this is important. So that's it. So now let's solve the following examples. Okay, so for each of the following given complex numbers, okay, we have to find letter A, the Cartesian coordinates, letter B, polar coordinates, letter C, polar form, letter D is the trigonometric form, and letter E is the exponential form. So let's start solving this. Okay, so let's start solving these examples. Okay, so for number 1, this is z is equal to 3 plus 2i. So we are asked here to solve for its Cartesian coordinates, polar coordinates, trigonometric form or polar form, tapos trigonometric form, and then exponential form. Okay, so the first question is the Cartesian coordinates. So the Cartesian coordinates are just the um, real and imaginary part of this complex number. So the real part here is 3 and the imaginary part here is 2. So that will be the Cartesian coordinates, 3 and positive 2. Now, the second question is the polar coordinates. So the polar coordinates, okay, we have to solve for the value of r, okay, and also we have to solve for the value of theta. Okay, so solving for the value of r, that is just equal to x squared, square root of x squared plus y squared, wherein x is the real part and y is the imaginary part. So solving that will just be equal to square root of r squared plus 2 squared. Okay, so the answer for that will be square root of 13. So this will be the r. Okay, now we also have to solve for the value of theta or argument. Now, before answering the value of theta or argument, you first have to determine, okay, the location of your complex number. If what quadrant, okay, it is located. Okay, so in this case, z is equal to 3 plus 2i. Since positive yung real part and imaginary part, it means to say that your complex number is located in the first quadrant, right? So in solving for its theta, it's just directly arctangent of y over x, right? So it's just in the first quadrant kasi. So directly, that will just be equal to arctangent of y, which is 2, over x, which is 3. So the answer for this will be 0.0.58800. So the unit for this is radian. Okay, so that will be the theta. Now for the answer for letter B, we are asked for polar coordinates. So that will be r and theta. Okay, so the answer will be r, which is square root of 13, and then theta, which is 0.58800. So this is how you write polar coordinates. R first, then theta. Okay, so this is the answer for letter B, square root of 13 and 0.58800. Now for letter C, we are asked here to find the polar form of this complex number. So in polar form, so it is expressed in r angle theta. So meaning to say we need r and theta. So we already solved the value of r and theta. We just substitute it to the form of trigonometric or polar form of complex number, which is r angle theta. So your r here will be square root of 13 angle, and your theta will be 0.58800. So this will be the polar form of this complex number. Now, for the fourth question, that will be the trigonometric form. Also, the trigonometric form is expressed as z is equal to r cis theta, right? So that's the shorter version of that form. So what we need there is only r and theta. So again, we already solved the value of r and theta. So we just substitute it to r cis theta. Okay, so the value of r is square root of 13, then cis or cis, your theta is 0.58800. So this will be the trigonometric form of this complex number. Now for letter E, we are asked here to solve for the exponential form. Now for the exponential form, that is just r e raised to theta I. So you just substitute the r and theta, solve from letter D. Right, so that will just be square root of 13 e raised to 0.58800 I. So this will be the answers for this item, no? Now for the second given, which is z is equal to negative 1 plus I. So it has the same set of questions, right? So for letter A, it will be Cartesian coordinates. So the Cartesian coordinates is the real part and imaginary part of the given complex number. So the real part here is negative 1, and the imaginary part here is positive 1, right? So that will be the Cartesian coordinates, negative 1 and positive 1. Now, to solve for the second question, that will be polar coordinates, we need r and theta. So to solve for r, that is just equal to square root of x squared plus y squared, wherein your x is negative 1 and your y is 1. So solving that, that will just be equal to square root of negative 1 squared plus 1 squared, and that will just be equal to square root of 2. So your r now is square root of 2. Now, also, we need to solve for the theta or the argument. But before solving your argument or your theta, you first have to determine what quadrant, okay, it is located. Okay, so in this case, since the given is negative 1 plus I, the real part is in the negative or in the left side, no, at the left side of the x-axis, and then your imaginary part is positive, so it's in the upper part of your imaginary axis. So meaning to say, this will be located in the second quadrant, right? So since this is located in the second quadrant, as we have discussed earlier in the arguments of complex numbers, so if it is located in the second quadrant, your theta will be added by pi. Okay? So since your theta will be equal to arctangent of y over x, and since your y is positive 1 and your x is negative 1, it will be negative. The value that will be produced here is negative. That's why we're going to add pi to solve for the theta. So to solve for the value of theta here, So this will become negative pi over 4 plus pi. So that will give you 3 pi over 4. So the unit for this is radian. So this will be the r and theta. So our polar coordinates therefore will be square root of 2 and 3 pi over 4. So now for the third question, which is the polar form. Okay, so what we need there again is r and theta. So we just substitute that to r angle theta. So this will be the r square root of 2 angle, and your theta is 3 pi over 4. So now for letter D, that is trigonometric form naman. So you just substitute that to r, your r and theta, you just substitute to r c theta. So your r again is square root of 2 and your theta is 3 pi over 4. Now for the last question, that will be exponential form. Again, you're just going to substitute your r and theta to r e raised to theta I. So that will be your exponential form. That will be square root of 2 e raised to 3 pi over 4i. So this will be the answers for number 1 and number 2.
So let's continue our discussion about the third example. So the third example, this is z is equal to negative square root of 6 minus square root of 2i. So we are also asked here the same set of questions. So the first one is the Cartesian coordinates. So in this case, the Cartesian coordinates, the real part will be negative square root of 6 and the imaginary part will be negative square root of 2. So that will be the Cartesian coordinates, negative square root of 6 and negative square root of 2. Now for polar coordinates, so again, for polar coordinates, we have to solve for r and theta. Okay, so to solve for r, that is just equal to square root of x squared plus y squared. So that will be square root of negative square root of 6 squared plus negative square root of 2 squared, which will be equal to 2 square root of 2. So that will be the r. Now, before solving for theta, again, you have to consider first the location or the quadrant where the complex number is located. So for this given, this is negative square root of 6 minus square root of 2i. So since the real part is negative, so it's in the left side of the x-axis, right? And since the imaginary part is negative square root of 2, so it means that it is located um, at the lower part of the imaginary axis. So meaning to say, our complex number here is in third quadrant, right? So for complex numbers in quadrant 3, the argument will be arctangent of y over x minus pi, right? So what will happen here is that the arctangent of negative square root of 2 over negative square root of 6 will be pi over 6 minus pi. So the answer will be negative 5 pi over 6 radian. So that will be the theta. Okay, so combining r and theta, so that will be your polar coordinates. So these are your polar coordinates, 2, square root of 2, and negative 5 pi over 6. Now let's proceed to the third question, which is the polar form of this complex number. So again, what we need here is r and theta. So substituting that to r angle theta. So this will be the polar form. Z is equal to 2 square root of 2 angle of negative 5 pi over 6. So that will be the polar form. Now for the trigonometric form, so also we also need r and theta here. So we just substitute that to the form or trigonometric form, which is r cis theta. So this is r and then cis, and then the theta is negative 5 pi over 6. So it's the same with number 5, which is the exponential form. So for exponential form, the exponential form is expressed as z is equal to r e raised to theta I. So you just substitute r and theta. So that will be 2 square root of 2 e raised to negative 5 pi over 6i. So this will be the answers for number 3. Now let's proceed to number 4. So the given for number 4 is z is equal to 1 minus I. Okay, so
The first question, again, is Cartesian coordinates. So for the Cartesian coordinates for this complex number, the real part is 1 and the imaginary part is -1. Okay, so that will be the Cartesian coordinates, 1 and -1. Now, for polar coordinates, we need to solve for the value of r. So the value of r will be square root of 1 squared times or plus -1 squared, which will be equal to square root of 2. Now for theta, so again, let's consider first the location of this complex number. If where we can what quadrant it is located. So since this is positive, the real part is positive and the imaginary part is negative. So meaning to say it is located in the fourth quadrant. Okay, so the formula for solving for its theta is just arctangent of y over x. So your y is -1 and your x is 1. So that will give you -pi over 4 radian. Okay, so now that will be your polar coordinates, square root of 2 and -pi over 4. So for letter C, so we just substitute r and theta to the polar form r angle theta. So for letter D, it's the same, no? So we just substitute r and theta to RC's theta for trigonometric form. And for letter E, we just substitute r and theta to the exponential form RE raised to theta I. So this will be the answers for number 4. Okay, so now for number 5, so this is z is equal to I. So we are asked here again to solve for the same set of questions. So for letter A, so we have to give the Cartesian coordinates. So for number 5, since this is z is equal to I, the real part here is 0, right? And the imaginary part is 1. So that will be the Cartesian coordinates. That will be 0 and 1. Now, for letter B, which is we are asked here to solve for the polar coordinates. So we have to solve for r and theta. Now, for r, so again, you just apply the formula that is r is equal to square root of x squared plus y squared, which will be equal to square root of 0 squared plus 1 squared, which is just equal to 1. So this will be the value of r. Okay, now for the value of theta, okay, so if you are going to use the formula arctangent of x y over x, that will be 1 over 0. So definitely this is this is undefined, right? There's no value for this even if you input this on your calculator, right? But class, you have to be logical, no, in this case. Okay, so we all know that z is equal to I if you graph that in the Cartesian or in the Argand diagram. Okay, so where can you locate that? Okay, di ba your complex number, this complex number z is equal to I, if you graph that, it will be located here, right? Since 0 yung real part niya, so it will be 0 in the y-axis, but there is 1 in the imaginary part, so it will be located here, right? So now, how will we be able to know the theta? Okay, so theta will be from the uh, positive x-axis to the y-axis, right? So that will be the value of theta. Now, is the value of theta here undefined? No, we have a value for theta for this, right? So the value for theta for this will be 90 degrees or pi over 2, right? So class, that will be the value of your theta. So it will be pi over 2 radian. So again, your complex number here is located in the upper y-axis or in the positive y-axis. Okay, so your theta will be pi over 2 or 90 degrees if it's in degree mode, right? So it will be pi over 2 radian. So your r will be 1 and your theta will be pi over 2 radian. So that will be the polar coordinates. Okay, now for letter C, so we are asked you to solve for the polar form. So you just substitute r and theta to your polar form r angle theta. So ito yun, 1 angle pi over 2. For letter D, again, you just have to substitute r and theta to your trigonometric form r cis theta. But since your r is 1, so kahit di mo na ilagay yun. So that will be 1 cis pi over 2. Now for letter E, that will be exponential form. So again, you just substitute r and theta to the exponential form r e raised to theta I. So this will be the answer. So this will be the answer for number 5. Now, let's also solve the following example. So, sabi dito sa problem, graph the following complex numbers in the Argand's diagram and find the area of polygon form in a complex plane. So, the complex numbers given are z1 is equal to negative 3 plus 2i, z2 is equal to 5 plus 3i, and z3 is equal to 6 minus 5i. So, we should first graph these complex numbers in the Argand diagram. So, when we graph these complex numbers, it will give you this graph. Okay, so for negative 3 plus 2i, so its graph will be located somewhere here. Okay, and for 5 plus 3i, its graph will be somewhere here. And for 6 minus 5i, it will be located somewhere here. So after we graph these complex numbers, we have to connect all the points, okay, and connecting these points, okay, it will form a polygon. So what for polygon is formed? So the polygon form here is a triangle, right? So we're going to solve now for the area of this triangle form, okay? Okay, so let's solve this. Okay, so again, what we are looking for this problem is area. Okay, so this is the graph of the area that we're going to solve. Okay, so for this, okay, so to solve this, we can actually use Heron's formula. Okay, but if we're going to use Heron's formula, we should determine first the sides of the triangle. Okay, the length. Okay, or the sides, all the sides of this triangle, we should first determine them. Okay, so because in Heron's formula, the formula here will be yung area will be equal to square root of s times s minus a times s minus b times s minus c, where s is equal to a plus b plus c over 2, wherein yung a, b, and c are the sides of the triangle. Okay, so we have to determine first the sides of this triangle. So we can determine the sides of this triangle by using distance formula, since we have coordinates, okay, for the points here in our graph. So we can use distance formula. So this will be the formula for distance formula. It's just square root of x2 minus x1 squared plus y2 minus y1 squared. So we just need two coordinates here to solve for the sides, okay, for the distance, okay, of the side. So let's say our distance 1 is this point to this point. So we're going to measure this distance using distance formula. So our x2 here will be ito will be 5. Okay, so the coordinate here, x coordinate here will be 5, and then y2 will be 3, since our y coordinate here is 3. Here, our x1 is negative 3, since that is our x coordinate, and for y1 that will be positive 2, since that is our y coordinate. So substituting those coordinates, okay, in our formula, that will give you square root of 5 minus negative 3 quantity squared plus 3 minus 2 quantity squared. So the distance that we can get from here will be square root of 65. So that will be the distance 1. This will be the distance of this side of the triangle. So we also have to determine the distance of this side and this side. So also using distance formula, so we just have to use the coordinates for this 2 points. Okay, so that will be square root of x3 minus x2 squared plus y3 minus y2 squared. Now for your x3, that will be positive 6, since that is the x coordinate here. And then your y3 will be negative 5, right? Since the y coordinate here is negative 5. Now again, the x2 and y2 is 5 and positive 3 respectively. So substituting those coordinates in our formula, that will give you square root of 6 minus 5 quantity squared plus negative 5 minus 3 quantity squared. So that will give you square root of 65 as well. So distance 2 is just equal to square root of 65. Okay, so it's also equal with your distance 1, right? As you can notice, no? Ayan. So now, let's also determine the distance 3, okay? The third distance of the triangle, which is this side, no? So we need the coordinates of this point and this point. So using again distance formula for this, so your formula will be x3 minus x1 squared plus y3 minus y1 quantity squared. Your again, I've already mentioned the coordinates for this, no? So just substitute those coordinates in this formula, and it will give you square root of 6 minus negative 3 quantity squared plus negative 5 minus 2 quantity squared, and it will give you square root of 130. So this distance 1, distance 2, distance 3, this will now be the distance of the sides of your triangle. So this will represent A, B, and C. So now, in order for us to apply the formula of Heron's, okay, in solving for area, okay, we need to solve for first for the value of S. So the value of S will just be A plus B plus C over 2. So your A will be your distance 1, your B will be your distance 2, and your C will be your distance 3. So that will just be square root of 65 plus square root of 65 plus square root of 30 over 2, and that will give you 13.76313. So that will be your S now. Okay, so substituting the value of S, okay, to the formula, okay, for solving for area, that will be area is equal to square root of S times S minus D1 times S minus D2 times S minus D3. So you can store that in your calculator so that you will not input it everything on your calculator, no? So just store that to your calculator and then substitute those values in our formula. So that will give you a 32.5 square unit answer. So since this is area, no, we will add square unit here ha, as the unit. Okay, so that will be the answer for this problem. The area is equal to 32.5 square unit. Now, let's proceed to the fundamental operations for polar form of complex numbers. Okay, so the fundamental operations here will be product and quotient. So as you can see here, there's no fundamental operation for polar form, that is addition or subtraction. Okay, so there's no such operation for polar forms in that case. Okay, so for product of polar number Z1, Z2, let's say your polar number Z1 is R1 angle theta 1 and your Z2 is R2 angle theta 2. So if you solve for its product, it will just be the product, okay, of the modulus. Our modulus are R1 and R2, so that will just be the product of that. And then angle, and then your thetas will just be added. Okay, so your theta will be theta 1 plus theta 2. So that's how you multiply polar forms, okay, or complex numbers in polar form. Okay, so again, that is just the product of your modulus or moduli R1 and R2 and just the sum of your theta 1 and theta 2. Okay, so that's how you multiply complex numbers in polar form. Now, for quotient of polar form of complex numbers, okay, let's say Z1 over Z2 and your Z1 is R1 angle theta 1 and your Z2 is R2 angle theta 2. So if you divide this, okay, so what will happen here is that you just have to get the quotient of the moduli, which are R1 and R2. So that will be R1 over R2. And for your angle, your theta 1 will just be subtracted to theta 2. Okay, so that will just be theta 1 minus theta 2. Okay, so that's how you divide complex numbers in polar form. Now, also for fundamental operations for trigonometric form, it's actually the same concept with your fundamental operations for polar form because it has the same coordinates, right? It's just r and theta. So what you have done in your r and theta in your fundamental operations for polar form, it will be the same here in fundamental operations for trigonometric form. So let's say for product of two complex numbers in trigonometric form. Okay, let's say these are the two complex numbers, z1 and z2. So if you multiply these two complex numbers, okay, what you're going to do here is just multiply the moduli, which are r1 and r2, and you just add the theta 1 and theta 2. So that will be cosine of theta 1 plus theta 2 plus I sine theta 1 plus theta 2. So that's how you multiply polar or trigonometric forms of complex number. And also for quotient, it's the same principle again, no? That if you divide r1 cosine theta 1 plus I sine theta 1 over r2 cosine theta plus I sine theta 2, what you're going to do here is just divide the moduli. So that will be r1 over r2. And then for your theta, it will just be subtracted. So that this will become cosine theta 1 minus theta 2 plus I sine theta 1 minus theta 2. So it's the same. Now, let's solve the following problem for fundamental operations for polar and trigonometric form. So we have here given z1 and z2. So your z1 is equal to square root of 2, angle of pi over 4, and z2 is equal to square root of 13, angle of 0.58800. So we are asked here to find z1 times z2 and z1 over z2. So this is product and quotient. So for letter A, that is z1 times z2. So that will just be square root of 2 angle pi over 4 and square root of 13 angle of 0.58800. So for the product of complex numbers in polar form, what we're going to do here is just multiply the moduli square root of 2 and square root of 13. So that will just be square root of 2 times square root of 13. And what you're going to do with the angles will just be added. So pi over 4 plus 0.58800. So this will now be the operation. No? So we just simplify that. So that will be square root of 26 angle of 1.37340. Okay, so this will now be the answer for letter A. Now for letter B, so this is quotient. Okay, so for the quotient of z1 and z2, that will just be equal to square root of 2 angle of pi over 4 over square root of 13 angle of 0.58800. So we just perform the operation. Okay, so what we're going to do here, since this is quotient, we just divide square root of 2 over square root of 13. And for the angles, we just subtract pi over 4 minus 0.58800. So simplifying this, this will give you square root of 26 over 13 angle of 0.19740. So this will now be the answer for this problem.
So that concludes this session. I hope you learned. So see to it that you have learned the intended learning outcomes for this topic. And also don't forget to answer the assessment task in the latter part of the course material uploaded. So study well, keep safe, and God bless.